This is Team Skanska's Productivity Improvement Study. For our Productivity Improvement Study, we chose the new student residence hall being built at Oregon State University. Oregon State is a leading research university located in one of the safest, smartest, greenest small cities in the nation, Corvallis. Situated 90 miles off of Portland and an hour from the Cascades or the Pacific Coast, Oregon State ranks high in sustainability, fourth among universities nationwide for using renewable energy, and first in the Pac-12 conference. University officials say more student housing is needed because of Oregon State University's burgeoning student population. Officials announced in November 2012 that Oregon State University achieved record enrollment with a significant number of transfer and out-of-state students. The university has commissioned Opsis Architecture in Portland to design a new student residence hall. The firm has performed numerous projects for colleges and universities in the past. The area highlighted here is the chosen location of the new student residence. The project will meet the requirements of the campus master plan plus city and state building regulations. The building will be designed to reach equivalent LEED Gold per the requirements of Department of Administrative Services. The current schedule for the project assumes a construction start in the spring of 2013. The building is scheduled for occupancy in fall of 2014. The project's budget will be in the range of $230 to $240 per square foot. The new student residence hall is configured to maximize open space on the site. The building massing is composed in an L shape with frontages along Washington Avenue and 13th Street. This reserves the interior of the site for a large quadrangle, which connects the new community to the McNary-Wilson-Callahan Residence Hall precinct and creates a clear pedestrian linkage to the campus core. The adjacent Oregon State University residence halls can be generally classified as simple, functionally adorned buildings. The new students' residence hall acknowledges this context, but has an elevated design character in accordance with its mission to retain students beyond the first year. The new residence hall's distinguishing stylistic element is the projecting bay. The living unit has been designed with an articulated exterior wall which, when organized along a double-loaded corridor, creates an alternating rhythm of bedroom and living room bay projections. This technique results in a more human-scaled building, effectively translating a block-long facade into a series of discrete residential frontages. The new student residence hall primary material palette is proposed in equal parts brick and cement fiber panels. Brick is utilized as a visual datum linking the two-story commons volume to the residential wing. Cement fiber panels represent the middle of the tripartite building organization. The two panel types are a larger uniform panel and a smaller 6-inch wide panel laid up in horizontal rows. Both panels utilize an open joint rain screen assembly and feature subtle variations in color and texture to provide visual depth to the facade. While both primary building materials are similar in unit cost and maintainability, cement fiber panels are significantly lighter, which results in less anchorage and structural support. Accent materials include stone and metal for the cornice elements and the sloped roofing and mechanical screening. The majority of the new student residence hall's roofing is a low-slope, built-up material shielded from view through the use of parapet walls. There are two feature roofs proposed, a sloping sanding seam metal roof over the community's major social space, the multipurpose room, and the fitness room roof, which is visible from above and may feature EPDM with Mexican river rock ballast. The metal roofing will be pre-finished to match the metal cornice elements. The new student residence project on the east side of Oregon State's campus will have an area of 85,000 square feet across its 5 floors. It will house approximately 300 students in rooms laid out as shown in this image. Each unit will include 6 beds, 6 desks, 2 sinks, 1 toilet, and 1 shower. It will be open to both first-year and returning students. Along with the dorm rooms, each of the 5 floors of the new student residence provides public bathrooms, a kitchen and lounge, and elevator and stair access. The first floor is unique in that it includes the resident director's apartment and student health services, while the second floor includes a laundry room. After starting the project in late June, most of the excavation was completed by mid-August, and construction on the foundation was beginning as shown in the image above. By late November, most of the structural work on the first floor was completed, along with the foundation as shown in the image. By mid-December, most of the structural work on the second floor was completed as shown. Most of the structural work on the third floor was completed by early January, as shown in the image. Here's an image of the fourth floor structural work, mostly completed by late January. By late February, most of the structural work was completed on the fifth floor, as shown in the image. Each floor took around a half a month to fully complete, varying due to unworkable weather conditions such as snow or rain experienced in the winter season. Here's an image of the current state of the project in late April. Mainly masonry on the exterior walls and interior work has been done between late February and the time this image was taken. There's also some steelwork that was done on the roof, which still requires additional steelwork and masonry, along with other finishing touches. There is also substantial work remaining to be done on the interior of the building. The two operations observed by our group for the project were masonry and steel framing. Along the western and northern faces, brick siding is being placed on the exterior of the building. Work on the exterior brick siding began on March 24th on the 3 extruding wall sections. The 3 sections were worked on sequentially by placing brick up to a certain height on the northern extrusion and continuing south along the extrusions, placing bricks up to that same height. After these sections were finished, the north face and remaining wall sections between the extruding west walls and north face were worked on simultaneously, starting on April 14th. These sections were not as wide as the previous extruding sections and allowed for the team to split into groups to work on the masonry. A mortar mixer is used to make the mortar that is placed in between each brick and holds the wall together. The mortar is comprised of 3 parts: water, masonry sand, and masonry cement, which are mixed together until they reach a pudding-like consistency. Too dry and it will be difficult to set the bricks in the mortar bed. Too wet and the brick will sag. Trowels are the small handheld shovel-like tools used to scoop, spread, and scrape away excess mortar. The existing masonry operation includes a crew of 3 bricklayers, 1 laborer on the scaffold with the bricklayers, and 1 laborer on the ground, operating the wall and the mortar mixer. The crew balance chart is classified into 3 types of work: effective, non-effective, and idle. Effective work is directly related to the unit cost and is the actual time spent by bricklayers laying bricks. Non-effective time defines other actions such as layout, mortar mixing, and lull operation. Idle time defines the times in which the worker is waiting or not performing any specific tasks. The crew balance chart of the existing operation shows idle time for the bricklayers as they wait for the new batches to be mixed and delivered to the scaffold. This was an obvious flaw in the productivity of this crew and is the rationale behind the adjusted crew size explained. The adjusted or improved crew for masonry operations consists of the same crew as before, minus 1 bricklayer. Removing 1 bricklayer from the crew mitigates idle time spent waiting for mortar. The reason for this is simple. The mortar batch and bucket size delivered to the scaffold remains the same in either scenario. Removing one brick layer allows more time spent laying bricks for each brick layer, giving the mixer more time to produce a new batch of mortar. By the time the crew of 2 bricklayers expend their mortar from the first batch, the operator is ready to deliver another. So even though there is one fewer bricklayer in the crew, the effective work time is actually increased. Doing this resulted in a unit cost savings of $6.95 per square foot. The comparison of productivity rates between the initial and adjusted crew shows that the crew effective work time of the adjusted crew increases by 11 minutes per hour, and their productivity increases by 1.7 square feet per hour, along with their unit cost decrease. Along the southern face of the north wing of the building, the new student residence features a 3-story window facade. Having this facade will help increase the effects of daylighting within the building, which adds to quality of the indoor space. The scope of work requires at least 2 steelworkers to erect the steel framing. The task requires measurement of the installation area as materials to be installed. Various hand tools are used to make adjustments to the framing in order to ensure that the glass will be installed properly later on. The framework is the most important part of the facade, since proper installation and sealing will ensure that the building is sealed from the outdoor environment. Having the JLG telescopic boom lift allows the workers to quickly access the section of the facade being worked on. This allows the transport of material from the laydown area on the ground to the work area much easier. A possible solution to expedite this process, outside of changes in the labor force, would be to utilize a prefabricated curtain wall system. The reason this method was not selected for the residence hall is likely due to size of the scope of work. With it only being about 1,000 square feet, utilizing a prefabricated curtain wall system does not improve the economies of scale. Currently, the project site has a crew of 2 steelworkers framing the facade. The 2 workers essentially work as a pair for this task. The steelworkers walk to the down area to unpack the box of materials and will inspect the material for any dents, scratches, or damage. Next, the 2 will carry the material to the JLG telescopic boom lift. One of the steelworkers will then raise the man lift to the work area along the facade. From there, the 2 steelworkers will take the appropriate measurements and prepare the surface for installation. The necessary adjustments will be made as the steelworkers install the framing material. After the frame has been installed, all measurements will be verified. The man lift is then lowered back to the ground, and the steelworkers will walk over the laydown area to repeat the cycle again. With the 2 workers performing the same tasks repeatedly in 2 areas, it would be beneficial to add an additional worker to the crew. Therefore, we have proposed 2 options that will now be presented for our proposals. We assume that a task can be split into varying increments, and we were not proportional to the number of resources assigned in the activity. This assumption is reasonable since the task can be completed independently by 2 workers, such as inspecting material. 2 workers can inspect different pieces, but it can to the overall task. We have also assumed that the laborers are permitted to give preliminary inspection of the material, but it must still be inspected by a worker. This ensures that an individual competent Our first proposal is to add 2 laborers to the framing crew. The 2 laborers allow the steelworkers to focus their attention to only preparing, measuring, and installing the actual steel framing system. The laborers will assist the crew by unpacking and carrying material to the man lift from the laydown area. In this case, we provided 2 laborers as opposed to 1, since the material needs at least 2 people to carry it between locations. This crew balance chart shows that the cycle time would be reduced to 13 minutes when the 2 laborers are added. There is quite a bit of idle time for the laborers since their main tasks are to unpackage material, inspect it, and get to the steel workers. In order to reduce idle time, the laborers can begin to unpackage additional boxes. This was not included in the crew balance diagram because it would potentially create congestion on the job site. With limited space, packaging materials and piles of prepared steel framing will clutter the job site over time. An alternate resolution would be to have the laborers assist other trades. For example, if the bricklayers needed more bricks, the laborers could carry those to their workstation during the idle periods of the Our second proposal is to only add one laborer to the crew. For this situation, we would have one steelworker working inside the man lift, while the other is on deck of the building that they are working on. This way, the steelworker on the man lift can work with the laborer to carry material, while the steelworker on the deck prepares and measures the installation location. The laborer would continue to unpackage material and help carry it with the steelworker to the man lift. Overall, this option provides the most efficient process for the crew, since the cycle time is only 13 minutes with only 3 tradesmen. A new constraint to keep in mind with this proposal is the safety of the steelworker on the deck. It is likely that fall protection will be required, and he will need to be tied off to a restraint line across the building's edge. Although he is tied off, it is just as safe for him to be working on the deck as it is on the man lift. The steelworker on the deck also loses the ability to work at a comfortable height that the man lift provides. He will likely need to squat, bend, and reach for the high and low positions for installation. There will also be additional equipment. In conclusion, the productivity of Oregon State University's new student residence hall can be increased by distributing labor so that idle times are reduced, assigning idle laborers to assist with other trades or current tasks, splitting up tasks to be worked on by smaller groups, and optimizing available space by properly scheduling deliveries and arranging equipment and materials in an organized fashion. In accordance with the diagram on the effects of increasing the productivity of the new student residence hall would decrease unit cost, making the construction company more competitive, and increasing the profitability, which has a positive effect on the staff, which then in turn further increases the productivity.